The Oak Island map looks simple at first glance. A large compass with strange directional arrows, a labeled historical landing point, and several meaningless or grammatically irregular French phrases. These elements appear rough, inconsistent, or even accidental. Most people assume the drawing is casual or symbolic rather than technical. It doesn't resemble modern engineering diagrams and doesn't match the treasure map imagery shaped by popular culture. As a result, readers approach the map interpretation with low expectations. They look at the elements as static rather than functional. The compass as directional, not as proportional tool. Symbols as meaningless decoration, not as geometric clues. The cues are subtle, and without a logical perspective, its technical nature remains purposefully hidden in plain sight. This appearance of an uneducated, hastily drawn sketch leaves the reader with a dismissive impression. This reinforces a long-standing stigma of forgery. Once something is labeled fake, most readers stop asking questions, never looking close enough to notice the drawing contains coordinated clues, directional cues, proportional relationships, and a specific unit of measurement all working together. The forgery narrative persists largely because it requires time and persistence to understand complexities, and usually any structure is assumed a coincidence rather than an emerging design. The Oak Island map is not a static treasure sketch, rather a mathematically constructed progression using known mathematical methods. The presence of these classical methods does not date the map to any specific era or author. These techniques were taught continuously in Europe from antiquity through the 1800s. Therefore, the application here simply shows the author understood well-established mathematical principles. Once the map is read as a technical document, the internal logic becomes impossible to ignore. The rough handwriting and unconventional phrasing stop being distractions and start becoming clues to a structured method. The map stops behaving like a static communication and begins functioning like a deliberate sequence, fitting together as a progressive set of instructions. What must be recognized before the intended structure becomes visible is to understand the map communicates through composite clues rather than isolated symbols. For example, the west arm pointer triangle in the quadrant is referenced directly in the small drawing, connected to the landing clue. The indicated Frog Island landing point marks a real-world geometric reference. The 1347 is not a year of arrival. Rather, the written French phrase 1347 encodes a specific measured distance. The quadrant, which dominates nearly half the document, is not a compass, rather a proportional framework that governs the entire layout. None of these elements require advanced mathematics, but they do require the reader to approach the hidden information as a coordinated set of instructions rather than a sketch. This shift in perspective is essential because the map's most important information is not expressed through any single mark. It emerges only when the written, directional, and geometric elements are read together. When the reader begins to see how these components interact, the appearance of carelessness, rough handwriting, and unconventional phrasing start becoming indicators of a structured method. To demonstrate this integration of elements, nowhere is clearer than where the landing clue and the quadrant converge into operational instruction to create a distance value by proportional geometry. Before the landing clue can be implemented, other clues need to be identified and their function determined. Like constructing a puzzle, pieces must be identified and fitted together. Missing pieces will obscure the geometric progression and hinder the design intent. When all the pieces are assembled properly, the big picture is revealed. To understand the landing clue and its function, we must separate its composite elements. The French phrase "en 1347" is translated 1347. The word "un," appearing at the beginning of the number, is grammatically incorrect for a chronological date. The word "mil" translates to 1000. Therefore, the word "un" becomes redundant. This error informs the reader this is not a date, rather a distance that will define the master scale. The proportional geometry concept is shown through a small drawing beneath the underline of the written number 1347. This drawing has a small triangle that can be associated with the quadrant's west arm pointer triangle. The landing clue is designed to work within the quadrant constructive framework, creating a single master scale measurement. This reference value will be used to calculate the distance values of the quadrant proportion segments. The drawing with a small black triangle illustrates a Euclidean geometry principle of proportional lines, called Thales' converging point theorem. This concept is applied when the quadrant framework reaches the black triangle on the west arm pointer, directly associated with the quadrant. This point is the initiation of the master scale line. This line is projected to another point that is developed at the intersection by set line and the fish symbol functions. These interpreted elements all work together to give meaning to structured information. When these elements are read as a unified system, the landing clue becomes clear. It encodes a specific measured distance tied to a proportional method that will repeat across to the map of Oak Island. Implications of the Oak Island map does not require the map to be ancient, nor does it require any particular historical provenance. It simply requires an understanding of the integrated nature of the clues and geometric progression. Once this is recognized, the map is intentional, reproducible, and internally consistent.